Maybe you don't consider everything I do as specific, but I know the definition of specificness depends on who you are. But nevertheless, we're going to look at specific distributions, and we're going to start with this normal distribution. There are many different well-known and named distributions out there. You can see them if you Google or find a collection of formulas. There are many different such small f's out there that has a name, and then there are infinitely many that doesn't have a name. The one we are going to start with having a name, that's the normal distribution. Here it is. It's a bell-shaped curve. Here's the formula. Actually, it's a bit funny here, right? Here is maybe a rather complex formula. You may find there's both an x, and there's a mu, and there's a sigma in this formula. And I made an explicit function here, f of x, which was living, as we say, which was existing more or less on the interval -3 to +3, right? That was, how can that be? Well, it's because I cheated a little bit. I cheated such that I actually used this one with the choice of mu equal to 0 and with the choice of sigma, and would then be the same as sigma squared. Sigma is the standard deviation. Sigma squared is the variance. I made this particular choice, and then I came up with a simplified version of the normal density function, which is this one. So here we can see the structure of the function. It's the exponential to -x squared. That's a sort of rather simple mathematical function that you could put into sort of mathematical analysis, like you would have been taught, I hope, in high school, or using plot it on whatever tools you have to plot it, for instance, by R or by your pocket calculator, and you would find that this is how it looks. It sort of tops up in 0. It goes down to 0, and when we pass 3, 4, or something like that, it's down almost at 0. It never becomes negative, but it hits more or less, sort of has an asymptote, it goes to 0 like that. That's the function. We have this way of expressing it, and it's not actually put explicitly in the book, so pay attention to it because we're going to use that throughout. That this is sort of the typography, you could say, the code for making a long story short, that we say, if we make this notation, we say that x is a random variable with normal distribution with mean mu and variance sigma n, sigma squared. Well, how can I say I said mean and variance, mean mu and sigma squared? Well, using those names, mu and sigma squared, actually was the same names as I used for something else, because actually these are just as such sort of constants in some mathematical function here. The mu and the sigma is constants in this function. I had a general term. I'm not going to write, I'm just going to show you. I used mu and sigma for the generic general definitions of mean and variance of random systems. And now I have a mu and a sigma inside this density. Luckily, these two things match in the sense, and this is, it looks a bit odd maybe for many of you, mu equal mu, yes of course, sigma squared equals sigma squared, yes of course. What it really says is that if I integrate from -infinity to infinity of x times this density function coming here, dx, then I get mu from the formula. If I integrate x minus mu squared, and this can be solved actually, it's a bit of math exercise, you can find that in some of my additional stuff if you want, but it's not the syllabus of this particular course to be able to do these things, but if you want to go for a bit of proof, this one actually becomes sigma squared. So it makes sense. So the mu and the sigma squared constants in the formula actually are the mean and the variance of the normal distribution. We have it in tables, and we have the normal distribution obviously in R. Now here's a plot, the same plot of the function. Note again that I say it's the standard normal distribution function, the mean 0, spread 1, standard deviation 1. This is what we see down here. This is the standard normal living on this interval. Actually, what we're going to learn and what we're going to use in practice when we work with the normal, in a sense, there is only one curve. It's just a matter of where we see it and how we sort of scale it. But all such curves can be shifted and sort of pressed to be the same curve. And this is illustrated in this plot by saying all normal curves, the general normal distribution has a top in the mean. And then to be, actually there's a small inconsistency here. Actually it should say mu minus sigma, mu minus 2 sigma, mu minus 3 sigma. It should say mu plus sigma, mu plus 2 sigma, and mu plus 3 sigma. Because if you stand in the mean and you step 1 sigma to the right, 2 sigma to the right, 3 sigma to the right, it's the same as standing for the standard normal as standing in 0 and stepping 1 to the right, 2 to the right, 3 to the right. I'll go back to this in a second and show you. If we, on the same plot, have two different ones, well, we can, if we show them, they have two different means. Mean 0, 0, mean 5, 5. Then, of course, they are different. But you can see clearly that if you shift them, they're the same. The same up to the shiftness. Also, they could have different variances, but having the same mean. And that's just like pushing it or pressing it or stretching it. So that's just a feature of this nice function, that the mu's shift the bell curve and the sigmas sort of stretch the scale of it. But basically, up to those two things, you could say up to shift and scale, it's the same curve. So if you took one of these curves and just changed the sort of the scaling of the plot, you would end up with the same curve. So all normal curves can be seen like this, if you want, in a more generic way, going from the center and then 1, 2, 3 standard deviations out, and that's it. Then basically we're 0. That's the normal probability curve. This sort of property of shiftness and scaling, we can use that explicitly when doing hand calculations with the normal, when playing around with the normal. That's a quite convenient thing to sometimes. It can be quite convenient. Usually we use Z for the standard normal. That's the one I just discussed. When you have something which is generally normal, you can turn it into a standard normal by subtracting the mean and dividing by the standard deviation. Then something that was sort of normal with mu and sigma squared becomes standard normal with 0 and 1. So we can jump back and forth between a general normal and a standardized normal. Let's do one example. We take the thing about the intelligence at the end. So just to have you teased up a bit about that one. Normal distribution appears a lot out there in real life situations. For instance, measurement errors. That has no sort of other sort of explanations than randomness. Often behave like a normal distribution. What is a normal really? It's something which is symmetric. Half of the time to the left, half of the time to the right. And it has a shape, it's quite specific shape, actually. But this symmetry property is a key one. Now, here's an example. We assume that we have a measurement error described by this distribution. It's a standard normal. We measure the weight of a single piece, as it says. What is the probability that the weight measures at least 2 grams too little? What is the probability that the weight measures at least 2 grams too little? I mean, this is the challenging part. I said that last time. take such a statement and put it into this formula. You have to keep your tongue straight in your mouth to try to find out what am I really asked about. And it's very easy is it really like this, or is it the opposite way, or what is it? I believe this is what I'm asking here. You may disagree. Not the case. Let's see if we can find, I believe I didn't know, so I have to do it here. Let's see if we can find this probability. I'll do it in two ways. I will do it the neat way first. The neat way is here, right? P norm, that's the probability distribution function of the normal distribution. And if you say nothing else, put no options to it, it assumes it's the standard normal, right? There are options for mu and for sigma squared, but it assumes 0 and 1 if you don't tell anything. So I run this one, and I get 0.0228. 0.0228, right? Let me just show you also that, of course, we could also find it in the tables. I wanted to go, this is the standard normal distribution in the book. Look at, here's the formula again. It's the left tail probabilities. It's a probability distribution function which is tabulated. There's a lot of values from this one function in the book. There are 2 pages of numbers from this single distribution. So it's just from this curve. A lot of points that you can read off. And you can see you have a z here. We want to read off -2, right? That was the task we were given. Fantastic. 2.0, right? Minus 2.01, 2.00, 2.01, 2.02, 2.03, and so on. But this was the one, 2.00, right? And we see the same probability. So but this is just the P norm. You could say this is P norm. So there's a lot of values from the P norm function given on 2 pages. Actually, you can find apps with these tables also. If you go to App Store and go for statistics, or you can find some free apps. So if you really, if you want to score a beer or something Friday night, it's good to have some percentiles and normal distribution and things like that with you on your iPhone or your whatever you have. Unfortunately, R doesn't come as an app yet. I'm sure some of you are into making apps. It could be a neat thing, not for making money, but for making friends, to make such an app. Let me do one more little question before we do the break. Related to the same example. What is the probability? 2 questions, sorry. We take these 2 questions, but we can do them rapidly. What is the probability that the weight measures at least 2 grams too much? That's easy. Because we can use, it's good to use sort of sketches, of normal distributions. Before we found out that this probability was 0.0228, right? Now I'm asked to find this probability. But that's the same, right? It's a symmetric function. So it's exactly the same. So it's still equal to the same number. What is the probability? Look at what we'll take that later. What is the probability that the weight measures at most 1 gram wrong? I think within plus minus 1, I would say. That's my question here. Well, different things we can do. We could take less than or equal 1, and then we could subtract less than or equal minus 1, for instance. Right? That would be the typical way of getting such an interval. Take up to and including 1, and then subtracting up to and including minus 1. Now I'll do it the neat way. I put this already. P norm 1 minus P norm minus 1. Please, the density function, of course, is symmetric here. D norm minus 1. Let's just look at the D norm. The density, it's a 0.24. But the probability function just to show you this. The probability function, of course, is not symmetric in that sense, because these are the two. It's the left probability between 1 is much larger. That's 84%, whereas the left probability of minus 1 is much smaller. But it's symmetric in the other sense that if I take the right side, 1 minus P norm. P norm is the left probability, you could say, to the left of minus 1. But if I go, let me take the left of 1 instead. Left of 1, that was a high probability, 84%. But if I go right to the right of 1, which is 1 minus P norm, of course I get the complementary. That's up 15% something, which is the same as being left of minus 1. So left of minus 1 is the same as right of 1. That's the symmetry of it. Let's finish answering the question. If I subtract these two probabilities, I get 0.683. Let us just for a sec see what we have found. We have found that approximately 95% is within plus minus 2 standard deviations, and approximately 68% are within plus minus 1 standard deviation. Here's the 68%. Plus minus 1 standard deviation is 68%, plus minus 2 standard deviations, approximately 95%. Right, because we had 2.3% in each end, so almost a bit more, but approximately, if we round off, 95%. That's what we found, and that's a good place to make a break. So let's do a nice break now.